presenting today the work of Rob Bredman, and this is chapter 5 of his thesis, the chapter that hasn't been written up yet. And we're beating him over the head, and we're going to get this out relatively soon, but it's nice results. It uses a very simple model, probably even simpler than Jerry Goldstein's model, but it works out okay. And I changed the title from a quantitative to a qualitative because I'm going to wave my hands. What I'm going to show you first is a piece of analysis that resolves a 30-year-old puzzle that all of us that measure energetic ion outflow have wondered about, and that is that the independent of By, the energetic ion outflow is biased towards the non-side. It's less biased at low Kp, and it's at high Kp, but at low Kp, the low energy electrons in the bottom, this one. Aren't computers wonderful? Thank you. Okay. So let's start off by talking about upwelling and outflow. I'm an observer, and so anything that's seen on fast polar DE1 Akebono cluster Viking and apogee of EPOP I call outflowing, because it's generally has more than 4 or 5 volts, and it probably gets to the plasma sheet. Anything that's observed in radars, DE2 and EPOP when it's near perigee, and from the DMSPs is basically upwelling. And this figure, of course, comes from Strangeway, and it emits 2 important things that I want to talk about. The first important thing is it doesn't talk about photoelectrons, which are everywhere, and those are just the same thing as more soft electrons. So you can treat photoelectrons as energy precipitation, except it's locally injected. The other thing it doesn't include is back pressure when the field line rotates out of the night side and is basically empty, and the ionosphere bounces up. That was the first result that came out of the Millstone radar in the early 60s, and it's reproduced by almost all ionospheric models. So, oh God. I've got it here. We need to see this because these are particularly important. I should have checked this. I apologize. Did it make it? No. Now. Okay, so what Redmond did as the first part of his thesis is he assembled a database of ion upwelling from DMSP. He took Rod Helis's instruments that have been flying on DMSP, and he took density and velocity and binned them. And he worked with Harrison and several of the other people down there to make sure that we didn't include data that had too many warts. The other thing we did is we focused on quiet times. By that I mean non-storm times. So we sorted on DST less than minus 50. Include some substorms, minor substorms. So this is the database sorted in invariant latitude magnetic local time. And then what he did is he took the DMSP electron precipitating data and defined auroral boundaries, a poleward and equatorward boundary, and sorted the data into auroral coordinates. So the white line is the equatorward boundary, and the inner white line is the poleward boundary. And the real auroral zone is not like that. It's squished on the day side and popped on the back, but this is just a representation. And he then wrote a series of papers, and this is the fourth or fifth in it, if he ever gets it out, analyzing this data. And it's a dynamic boundary related coordinates is a productive way to do analysis of ion upwelling. The first thing that pops out when you do an analysis is this. This is not the best illustration of the downward shift. This is for Kp less than 2, and you can see it's over here. This is for Kp3, and it's here. Earlier in the day, Yao showed a RIMS data, a RIMS plot of that was really 600-volt electrons, and it was really far over. This shows up in the dynamic boundary-related coordinates. And after you think about it, what it is we have this upwelling on the dawn side where the empty flux tubes coming around to the day side hit by photoelectrons, pushed up. And so that's the biggest flux on the day side is dawnward, but the energy source is associated with the cusp. So the shifting back and forth is associated with the dawn source and the dawn upwelling and the noon energy source. Well, we didn't want to let him get off this easy, so we said, well, why don't you try a model? And we didn't want to do a big model, so we coordinated ourselves with Phil Richards, who has a field line interhemispheric plasma model that's not unlike what Shunk talked about today. It's a two-stream model that basically has been around for a long time. And what we do is we follow 40 flux tubes, not 1,000. We put three in the aurora. So the reason we do this is so flip is cast in geographic coordinates, and we've got to do the analysis in dynamic coordinates. And so we let these flux tubes rotate around. When they're in the auroral zone, we turn on precipitation, and when they're out, we don't. And we have 8 local times, 3 in the auroral zone, 1 pole and 1 equatorward, and we use Newell's ovation prime model. Yes, this does not include convection, and I'll address that, but it does include precipitation. So we do that, and this is the data again, and this is with the ovation prime model here, and this is with no aurora. And this is gross disagreement. This gray stuff here at 2100 is downwelling, and the data in that sector are upwelling. So there's some missing energy that's not captured in our model framework. So what is it? Is it precipitation or is it convection that we left out? Well, what Rob did is he went and took for DST less than minus 50 for the same time period as this data, he took and binned the 1-minute AMI potentials, and it shows it shows maxima in Joule heating or convection heating at dawn and dusk and noon, as you expect, but a minimum. Now, this is not the normal patterns you see because this is non-storm time. Most people don't think about that. So this is strike one. This says, well, perhaps convection and Joule heating is not important in that local time sector. The other thing we have is dispersive Alvfén waves, and they accelerate electrons, low energy electrons, and they show up in about the right spot. So we decided to go after and look at electrons, and what we did, this is the ovation prime model. Now Newell does this, he breaks it down into inverted V's, Alvfén waves, diffuse aurora, and total. We use the total. On the left is the characteristic energy. Where it's gray, it's greater than a kilovolt. Where it's black, there's no data, and this is the precipitation. You'll notice that all along here, it's over a kilovolt. So that, we think, is high. So what we did is we fudged with the model and said, what do we have to do to the precipitation pattern to get agreement here? And this is the with downwelling, and we got here. This is what we called was best fit. It's okay. And this is the characteristic energy. You'll notice that this is a 300 volts, so this is on the order of a couple hundred volts here, characteristic Maxwellian, where in the Ovation Prime it's calling it a kilovolt. And we kept the fluxes within a factor of 2. I have linear color bars here, so they lie a little bit, but we did that. And so based on this analysis, we say that the dynamic boundary layer coordinates are a new tool. The low energy 100-volt electrons are a significant driver of O+ upwelling in the night side. We didn't have to play with it on the day side. Almost anything we did, including no precipitation, worked. And the DMSP electron observations and the models derived for them significantly underestimate 100-volt electrons, which are very effective in driving upwelling. So what are the consequences for models? Models use simplified parameterizations upwelling, and some of them don't use anything. They just suck everything out and assume that the ionosphere follows blindly what the magnetosphere tells it. Somehow I think that there must be exceptions to that. These parameterizations in particular do not capture MLT variations. We saw that the dispersive Alvfén waves have a different local time distribution than the diffuse, and therefore the geo-effectiveness, and using only the inverted V electrons or the night relation probably doesn't get the ionospheric heating right. So what's probably missing in models is a adequate representation of the importance of the day and night side upwelling. And I've looked at quiet times. I know that at active times, all bets are off. The night side's probably more important, but it's yet to be proven. And that's it.
Questions?
I wish I listened to this very carefully, but maybe my comment is relevant, and that is that when you look at fast data and you see Alfvénic auroras, which are very often in the substorm precipitation, they're always not always, but most of the time accompanied by ion conics, because the waves which are generating the aurora also interact with the ions.
Yes.
So, okay.
But the game we're playing here are global models. And the fast data are way too complex and too hard to parameterize. So
it just all makes sense what you said.
Oh, okay. Yeah, I think this is an appropriate way to look at the problem.
When you determine the characteristic energy from Ovation Prime, do you do that for the composite distribution, including diffuse, monoenergetic, and broadband, or do you do that separately for each species? Because each of those populations will impact the ionosphere differently, but if you add them all together as a composite population, it's going to have a different effect.
Well, yes, and yes. He ran it every which way. He ran it he ran it no aurora. He ran it total. He ran it diffuse. Did
he run it wave only? Because wave only is the one that's going to do the upwelling.
No, because the fluxes here are small.
Yeah, but
and the energy here is a kilovolt.
But the diffuse and the mono and the total are going to be.
See, I chose my color bars to drive the point home. Yeah. Everywhere you see gray here don't count for upwelling. Yeah. And what's more, we've had discussions with Newell, and he admits that if he had more money, he could get a better representation of the low energy electrons.
Okay. I would just like to mention that if I had more money, I could get a better representation too, but.
If I second that, and if I had more money, I could have a scotch right now.